In this video, we're going to learn how to factor special cases. The methods for factoring special cases, at least some of them, aren't really too different. It's just our end result looks a little different than kind of what we're used to. So here we have a quadratic trinomial. We notice that the leading coefficient is 1. So if we decided that we wanted to use the shortcut, we could. But let's go ahead and take a look at what we're trying to do here. So leading coefficient 1, so we're going to multiply 1 and 64 to get 64, and then 16 there. So we know that the back sign is positive and the front sign is positive, so that means we're going to get two positive numbers. So we're looking for two numbers that multiply to 64 and add to 16. Well, if you know the 64 is a perfect square, and we know that its square root is 8, and 8 times 8 is 64, and also 8 plus 8 is 16, so it's going to be 8 and 8. Now, if we went through the whole process of doing factoring by grouping, this would be x squared plus 8x plus 8x plus 64. We split and factor, so the common factor in this is going to be an x, so we'll have x plus 8. The leading term is positive, so we're going to take out a positive. Those have a common factor of 8. Then we're going to have x plus 8. And we result in our first group being x plus 8, right? Those are what they have the same. And our second group is also x plus 8. And this is really what kind of makes it a special case, is because our two factors happen to be the same. Now, if you recall, what can you do when you have two things that are multiplying that are the same? Well, we can actually rewrite this as x plus 8, that quantity, squared. So this is a squared binomial in this. Now, we could have actually gone straight to this from here, and that the only reason that would work is because, again, the leading coefficient here in the beginning was 1. But this result is really what we are here for, and it's this squared binomial. And we call this trinomial a perfect square trinomial. So what if we have something like this? What if we have something like this? Now, the clues that we might have a situation like this are if your first term is a perfect square and your last term is a perfect square, we might end up with a perfect square trinomial. Now, that's not necessarily always going to be the case, but let's see what we have here. So if this is factorable, we're going to go 9 times 4. Since the leading coefficient is not 1, we can't use that shortcut. So what is 9 times 4? That's 36. So we're looking for two numbers that multiply to be 36 and add to be 12. Now the back sign is positive and the front sign is positive, so both of these are going to be positive. And what are numbers that multiply to be 36 and add to be 12? Well, again, 6 and 6, so it's the same number in both of these. Now we cannot jump to the shortcut saying x plus 6 and x plus 6 because this does not multiply out to be this. So we have to go through and factor this by grouping. So we're going to rewrite this and factor by grouping. So we're going to have, let's go ahead and do this. So it's going to be 9x squared plus 6x plus 6x plus 4. So let's split these terms and do our grouping. So split and factor. So what do these have in common? They're both divisible by 3, and they both have at least x to the first. So 3 times what gives me 9? 3x times what gives me 9x squared, so that's going to be 3x. 3x times what gives me 6x? Well, it's going to be times 2. The leading term here is positive, so we're going to take out a positive. Those have a 2 in common. 2 times 3x is 6x, and then 2 times 2 is 4. So again, we have 3x plus 2 here, 3x plus 2, and then on the outside, we also get another 3x plus 2. So again, we have the same binomial multiplying itself, so we can rewrite this as 3x plus 2 quantity squared. So this would be that factored. I would accept either of these, actually, because they mean the same thing. But this is what essentially makes it a special case. Now, there's one more type of special case that I want to look at, and it is this. Do you guys remember what we called these? These were a result of multiplying a certain type of situation And we resulted in something called a difference of squares. Now again, remember it's called a difference of squares because there's a difference, we're subtracting, and each of these terms is a perfect square. So this is really like kind of beyond what we had thought of or looked at before, because remember we had trouble with 3 terms. We needed to figure out how to write 3 terms as 4 terms, and now we only have 2 terms. So how do we do that? This can actually be expressed as something in the form of ax squared plus bx plus c. This is the standard form equation for a quadratic. So we need to figure out what we can write as our middle term. So what can I add in here in my middle term that wouldn't change its value but would just change the way that it looks? Well, what can you add to anything that doesn't change its value but could just be something that changes its look? Well, that's 0. So I need to put a term in here that has a value of 0. So I can basically take this, rewrite it as y squared plus 0y minus 64. So now we have 3 terms. So again, we're looking to find 2 numbers that multiply to be negative 64, multiply to negative 64, and add to 0. Now our back term is negative, so that tells me 1 positive, 1 negative. So what are factors of 64 that add to 0? Now, how can you have 2 numbers that add to 0? That only happens when your 2 numbers are opposites, meaning they have the same value but opposite signs. So what number, when multiplied essentially by itself, by its opposite, gives me negative 64? Well, that would be negative 8 and positive 8. 8 times 8, negative 8 times positive 8 is negative 64. Negative 8 plus 8 is 0. Now, because my leading coefficient is 1, I could jump straight from this into the y minus 8 times y plus 8. Otherwise, you can set up your factoring by grouping like this and go through that process, but you're going to still just end up there. So a difference of squares that we have here, right? When you have a difference of squares, you result in when factored, a product of 2 conjugates. So remember, conjugates are where the first terms are the same, the second terms are the same, and then the only thing that's different is the sign between them. So whenever you have a difference of squares, you end up with a result where you are multiplying conjugates. So let's look at this last example. So this last example is, again, 2 perfect squares, 4x squared and 36. And so we're going to have a situation here where we are looking for 2 numbers, where we're trying to rewrite this with a middle term and essentially factor, right? Now, one thing that we, again, always need to consider, and I didn't really talk about it in these other problems because none of them had this, but the first thing that you should always consider, always ask yourself when factoring is there something that all of these terms have in common? Is there a common factor that I can factor out? Now, if you didn't recognize that this had a common factor, you're going to end up with larger numbers and it's going to make the process a little bit more difficult. It's still doable, but it's going to make it a little bit more challenging. So these actually have a common factor of 4. I can actually take a 4 out of both of these, and I end up with x squared minus 9. Now, in doing this, I still end up with a difference of squares. X squared is a perfect square, 9 is a perfect square. So I can still factor this the same way by thinking about this as 4 times x squared plus 0x minus 9. So we're looking for numbers that multiply to be negative 9 and add to be 0, right? And what would that be? So if the back number is negative, that means we have 1 positive, 1 negative. 2 numbers that multiply to be negative 9 and add to 0. They're opposites. It's going to be positive 3 and negative 3. And we end up with, again, in this here, the leading coefficient is 1. So we're going to have 4 times x plus 3 and x minus 3, right? We have the shortcut that we can use. Now, what if you didn't recognize that it had that difference in there? What could you have done? Or that common factor? Well, if we did that, we'd have something like this. 4x squared plus 0x minus 36. Then we'd have to multiply. So you take 4. Let me do this. You'd go 4 times negative 36. That's negative 144. So we're looking for two numbers that multiply to be negative 144 and add to 0. That would be negative 12 and positive 12. And then you're going to rewrite this. So it's going to be 4x squared plus 12x minus 12x minus 36. Split and factor. So this has a common factor of 4x. 4 times 1 is 4. And then x times x is x squared. 4x times 3 will be 12x. So we'll have that. Now, the leading term here is negative, so we're going to factor out a negative. These both have a 12 in common, so I'm going to factor a 12 out. And then negative 12 times x is negative 12x, and then negative 12 times a positive 3 would be negative 36. So these are the same, so x plus 3, that's our first group. And then our other group is this here, 4x minus 12. Now you might notice that this doesn't match this perfectly. And there's a reason. Because this here, right, this term here has a common factor in it. This can be rewritten as 4 times x minus 3, right? If I factor out a 4, that's another way that we could write this. So really, we need to factor that 4 out, and then we'll end up with 4 times x minus 3 times x plus 3, which would be essentially the same as what this is. You can move these pieces around because of the commutative property, but the result ends up being the same.